I'm gonna go ahead and create another function, plot protein sparsity. So we're gonna get the protein data frame here. Have another data frame as the output. So basically we want to check how many dysfunction checks how many zero values each protein has. I'm going to define protein sparsity to be everywhere that protein data frame is 0. And then average over, this will treat true as 1 and false as 0. This will be a bunch of true false. And then this is gonna like get a mean over all of it. And then I'm gonna sort them. Let's say descending. So by doing this, we're gonna put the most sparse proteins first. And let's see what's inside this. All right. So if the number that you see here is close to 1, it means this protein has barely expressed, because it's almost every cell has 0, right? And the more we go down, we're gonna see the proteins that are almost expressed everywhere, because no cell has 0 of it, right? This kind of shows the fraction of cells that have 0 counts for each protein. If you're a biologist, you should be able to tell if these two, for example, proteins, like why every single cell has some of these at least, right? If a protein is expressed everywhere, this means it's low sparse. So we want to keep them. But the problem-making ones are the ones that are not expressed everywhere, and that they are highly sparse. So now let's plot this. We want to bar plot with a size and 5. Y label. Fraction of cells with 0 protein count. And then the title would be protein target sparsity. And we're going to rotate the protein names so they are kind of readable. 90 degrees. And we're going to adjust plot spacing, title layout. And I'm going to save this. Yeah. Oh, sorry, I think this must have another name. Size. Is it like fake? Yeah, cool. So what we want to see here is either like a dense data set where all the bars are very low, or like kind of this, it's like a clean step pattern, like the 1 and then there's 2 and then 3 and then, you know, it comes down. So like most markers, or in this case proteins, clustering low. This is acceptable as long as the majority of proteins are in the low sparsity region. But the only one that is really problematic is CD34, because it's an extreme outlier and we're going to probably remove it. Everything else being below 0.2 is like, my model will have plenty of real signal to learn from across almost all 28 proteins. So I'm going to go ahead and try to remove those proteins that are above, has a protein sparsity of 0.8 and above. So high sparsity. Or I can, let's say, keep all the ones that are less than 0.8, and so we're just going to keep low sparsity, and then we'll return protein df. Now let's move on to checking protein variance. going to create a new function. Or I'm going to go and let's clean this a little bit, looking better. So this function we'll see how much each protein varies across cells, right? We're going to define protein variance to be, there's the function there, and we're going to calculate it over the 0-axis and down the row for each column, and we're going to sort it. If a protein has high variance, it means the protein changes a lot across cells, right? So let's print them and see what's inside. So the higher the number, the more variation across cell, more information for the model. So as we see, CD11B has the highest number here, varies enormously, strongest signal. I think if we go back to this plot, B here, yeah, this guy has varies enormously, perfect. And other biomodel proteins have high variance too, right? So let's say CD3, these must have, yeah, 3.99, perfect. That's confirmed. Now let's go back and plot this. Again, I'm going to do something like this, but this time with variance. Protein. Okay, that's a variance. And here again, variance. So let's run this. Okay, we have CD34 and, oh sorry, this is fraction. There is a smooth continuous decline from left to right. I don't see any dramatic cliff or gap like the one we had, with this like shoot. So this point will tell you where to cut, right? But we don't see any of that here. Maybe a little bit here, but still kind of continuous. But we can maybe split this into 3 tiers. The first one is up until here, where you have anything above 3 variants. These are technically star proteins. They vary enormously across cells, meaning the model has a rich signal to learn from. These proteins will likely have the best prediction accuracy and drive most of the biological insights. The moderate variance could be like up until here, anything up until 1.5. And this is like, solid, usable proteins. But the rest is gonna be kind of like low variance. But an interesting insight from this plot compared to, given all the things that we already know, is that this CD15 right over here is the lowest variance, but almost 0 sparsity, as we saw before. Almost 0 sparsity, meaning almost every cell expresses CD15, but they all express it at roughly the same level. It's not 0, it is just flat and uniform. This is different from CD34, for example, which is 0 in most cells. So for the model, something like CD34 would be hard to predict because almost always 0. CD15 is hard to predict because almost always the same value. Both end up being poor prediction target, but completely different biological reasons, So at this point, because our dataset is not that huge, some people might want to keep everything, don't remove anything, low variance proteins. Kind of thinking like maybe let the model figure out what is useful. But some people are like, okay, this is garbage in and you're gonna learn nothing from this. If we remove it, we might want to use a simpler model. If we want a simple model or like a faster training, we will probably want to move low variance. But if we have a model, we want to design a model that handles irrelevant features well, or just want to be like conservative and not throw away anything, then we want to keep it. Personally, I would like to keep it because still I think it can introduce some things. But also we can do something else which is kind of more practical, only removing if both high sparse and low variance. In our case, CD34, this guy clearly failed both tests, so I just take this out probably and leave the rest. Before I forget, just make sure when you plot the fraction cells or variance, you plot them based on the logged version of your data, because raw counts have a well-known problem called mean variance dependence. Proteins with higher counts automatically have higher variance, just because the number is bigger, not because they are biologically more variable. So it's best if it's a better practice if we first log and then we plot and see variance and everything. or even sparsity, is just counting zeros, right? And so log of x plus 1, and if x is 0, log of 1 equals 0. So 0 stays 0 after transformation. The sparsity calculation gives you, identical results whether you compute it on raw or log data. So yeah, I just wanted to mention that as well. It's a better practice. So now let's go ahead and take a look at protein correlation. This is interesting because proteins are not independent. Some are markers of the same cell type. So I'm going to plot protein correlation. Checking correlation between protein targets. So we're going to define protein or to be protein df dot using core function. I'm going to use Spearman method. Spearman is good when relationships are not perfectly linear. And then let's fix size. We don't forget that. So I wanted to show the plot as an image or a heat map. So I'm going to use imshow. I'm going to add a color bar so we know what the color means. And of course I want the protein names to be on the x-axis. The number of it is going to be the length of protein correlation columns. And of course we want to rotate it 90 degrees. And then again another time we want to put the protein names on the y-axis as well. But we won't rotate it this time. Writing the title, the protein Spearman correlation. I'm going to adjust spacing, and we're going to save it. Right, let's run. Alright, so now let's read this. So 1 technically means perfect positive, right? If high x always means high y. So the correlation here, for a little bit of context, a Spearman correlation here means do cells that have high x also tend to have high y. So x is proteins and then y is also proteins. So we're really asking if certain protein is high, will other proteins in relation to that will be high as well or no? So if you're 0, this means technically no relationship, at this green. This must be teal. And if you are closer to -1, then it's like the opposite. So if there is higher x, there is low y. And of course the diagonal is always going to be 1 because every protein has relations with itself. If we look at the top left region here, we can see that they're mostly in the color on this spectrum. So this means they are all positively correlated with each other. They probably tend to be expressed together in the same cells, right? If you're a biologist and you're watching this, I would love to get some insight to see what does CD80, TIGIT, these represent, and do they actually, express together in the same cell? On the other side, we're seeing some sort of mixed colors. We have very dark purple one, for example, here it's CD45RO and CD45RA. So these are negatively correlated, as you see, there are squares of dark purple. But we also have very yellow colors here and here. So it's kind of a mix. Yeah, but this is very interesting. It's too dark to not notice. And so I'm guessing these two proteins are gonna be mutually exclusive. So it's gonna be one or the other. But what does this tell us, in general about our model? What can the model predict? The strong positive clusters can carry redundant information. So predicting one of them helps predicting the other. The strong negative pairs, the model needs to learn opposite patterns, right? 3, we should also make sense of this in biology, if it makes sense at all. Otherwise, our data is not clean. And if there is non-zero correlation, those proteins are independent, so they need a separate learning signal. Now, I want to make a UMAP for rRNA, but before that, let's go ahead and push this on GitHub. First of all, let's ignore everything that has PNG. That's it for this video. I hope you enjoyed it. and I'll see you in the next one.